In this lesson, we're going to learn about hypothesis testing on one proportion. We're going to use the example below to help us out with navigating what we need to do and the steps that we need to complete in order to perform the hypothesis test. So the scenario says we'd like to determine if fewer than 75% of people would continue to watch a TV show after viewing the pilot, which is 4 episodes, on average. To investigate the statement, we took a simple random sample of 100 people and found that 70 people responded that they will continue to watch the TV show, while 30 people responded that they will not watch the TV show. To evaluate this, we'll use a 0.05 level of significance. Now, there's a couple things that I want to point out. Number one, when we're talking about evaluating some sort of claim, which the claim or the statement or the question that we're looking at is up here. When we talk about this word evaluate, this is really screaming, do a hypothesis test. And then the claim that we're trying to evaluate is if fewer than 75% of people will continue to watch the TV show on average. So this 75% right here, that's the hypothesized value of our population proportion. And we refer to that as P0 or P sub 0. And we typically express that as a decimal because we're going to use it for computational purposes. So that's going to be P0 is equal to 0.75. Now, in here we also reference that we took a sample of so many individuals and there were different ways that they responded. So we can calculate a sample proportion. If you recall, in order to do that, our sample proportion is equal to X, the number of things with the characteristic we're interested in, over N, which is the sample size. N is pretty easy to identify because in there it explicitly states that the sample size is 100, but the value of X is a little bit trickier to identify. Now this is really important. When we're talking about this population proportion, remember this 0.75 represents people who would continue to watch the TV show. And when we talk about the sample, we need to make sure that the values for the sample match up with what we're trying to study in the population. And in here it says 70 people responded that they will continue to watch the TV show. So that way we have the same group that we're comparing right there. We would not want to use the 30 because those are individuals that will not watch the TV show. So our value of X in this example is going to be 70. So we have 70 divided by 100, which is 0.70. Now you might be looking at this and saying, okay, the sample proportion is indeed smaller or fewer than the 75% or the 0.75 that will continue to watch a TV show. So can't we just jump to the conclusion right now and say fewer than 75% of people will continue to watch a TV show? Well, the one thing this singular value does not account for is variability from sample to sample. Remember, we're trying to determine if on average, the majority of the time, this value is going to be less than 75%. If we had a bunch of you as students go out there and take your own independent random sample of 100 people, we would not all come up with the same value of 0.70. Some would be higher than that, some would be lower than that. And when we go through and we do this hypothesis test, we're trying to see if we're consistently higher than 0.75 or consistently lower than 0.75 or exactly 0.75. The steps that we go through next are going to give us a better tool to evaluate this statement and determine if there's statistical significance that we have fewer than 75% of people that would continue to watch a TV show. One of the first things we have to do before we jump into doing the hypothesis test is we have to go through and verify that we meet the conditions in order to perform the hypothesis test for this situation. So if you think of like a flow chart, this is kind of like our flow chart. It's narrowing it down to the most appropriate hypothesis test for the information that's given in the problem statement. We already talked about this in class, so I'm not going to go through it in detail. But in general, we're going to ask ourselves, what type of variable do we have and how many do we have? What type of parameter are we estimating? Or what type of parameter are we evaluating? So in this case, we have a categorical variable, which is people who will continue to watch a TV show or who will not continue to watch a TV show. We're interested in the ones that will watch. We have a defined population proportion, which is the proportion of all people who will watch a TV show. By answering that question right there, we've narrowed it down to potentially the binomial test for the proportion or the hypothesis test on the proportion using the z-distribution. So we have a 50-50 chance if we were to guess right here. The second assumption is there to ensure that we have a random sample. In other words, we want to reduce or eliminate as much of the bias as possible in the selection process for sampling, so that way we don't have biased results. If we have biased results, we can't really generalize that out to the population. And that's our goal in the end, is to be able to take this information and generalize this to the population. The third condition is asking, is the sample size large enough? And if the sample size is large enough, we can use a normal distribution, the Z distribution, in order to approximate that. And this happens when we have 10 successes and 10 failures. And I show the computation below. You can see in both of the computations that we exceed 10 successes and 10 failures. So that's saying, yes, we can use the normal distribution. So this last condition right here tells us we can either use the normal distribution or we can use the binomial distribution. We satisfy the requirement to use the normal distribution. So moving forward, we're going to do the hypothesis test on the proportion using the Z distribution. Now we're going to take a look at writing the hypothesis statements, but before we get to that, I like to draw pictures to help us visualize what's going on as we go through and do this. So I'm going to draw a picture of the normal distribution so we can see some of the stuff in this normal distribution. So this is also known as the Z distribution, and the mean of the Z distribution is 0. We've talked about that. And now we're ready to start taking a look at the hypothesis statements. Now, if you recall, H sub 0 is always a statement containing equality. So we have to use symbols like less than or equal to, and greater than or equal to in H sub 0. In H sub A, these are always statements about strict inequality. So we're going to use symbols like greater than, not equal to, or less than. And the hypothesis statement always has something to do about the population proportion, at least in this one right here. In other chapters of the text, we'll talk about other parameters that we're evaluating, but we're evaluating the population proportion P, so we might as well go ahead and write that down. We also know that this 0.75 is our hypothesized value of the population proportion, so we're going to be evaluating this population proportion as it relates to this 0.75. The last thing that we need to do is we need to determine how we're going to evaluate that statement. What are maybe the conditions or the criteria for evaluating that? And I'll give you a big hint. If you remember that the symbol that goes in between the P and 0.75 has to be one of these 6 symbols right here. One of these 3 specifically in H sub A and one of these 3 specifically in H sub 0. We can probably look through the problem statement and find the appropriate symbol. And if you read in that first line, it says we'd like to determine if fewer than 75% of people would continue to watch the TV show. That is saying that we're looking at the case where this is less than. And that symbol can only go in the alternative hypothesis. Now, when I teach this the first time through, the hypothesis testing the first time through, I always like to use the complement rule because I think it's easier for students to understand. So since we're using the less than sign in H sub A, we're going to use the complement pair, which is the greater than or equal to sign in H sub 0. Now, if you stop and you think about this, again, this is just a visual representation of what's going on with the hypothesis statement. Our population proportion can only be between 0 and 1. It can't be any smaller than 0 or any larger than 1. And our hypothesized value is 0.75. And if you think about these statements, we can look at H sub 0, and H sub 0 is really saying the population proportion could be 0.75 or it could be larger. But remember, the largest it can be is 1, so that's why I'm putting this vertical green line right there. And this would represent H sub 0 right there. H sub A is saying the value of the population proportion is smaller than 0.75. And if you remember when we graph inequalities, if it's a less than symbol, we leave an open circle, meaning it's not including that value. And we will go to the left. And again, it can't be below 0, so I'm putting a little vertical line right there so we recognize that. And this is representing H sub A, where P is less than 0.75. And if you look at this picture on the number line, these are all the possible values that the population parameter could take on. And we're really asking the question, is the population parameter greater than or equal to 0.75, or is it indeed less than 0.75 for the alternative hypothesis? Only one of those 2 statements can be true. In other words, only one of those 2 statements can have evidence that supports it. Now, the alternative hypothesis is extremely important. It's going to tell us whether we have a one-tail test or a two-tail test. And if it's a one-tail test, it'll tell us which tail we're testing. So if you look at the symbol in between the P and the value, that's a less than symbol. So this is telling us we're doing a left tail test. And it's very simply because that arrow in H sub A points to the left. If it were pointing to the right, we would be doing a right tail test and we'd be testing the tail over on the right side of it. And if it's a not equal to, we'd be doing a two-tail test. And I'll talk about the not equal to sign later on. It also tells us that this area in the left for that left tail, this is telling us this is the reject H sub 0, our null hypothesis region. So that's where the criteria for rejecting our null hypothesis. And then the area to the right of this, we refer to this as the fail to reject the null hypothesis region. So that alternative hypothesis is really important for the setup of this problem. And we're going to come back and we're going to use this a few other ways. So moving forward, I'm going to bounce back and forth to this normal distribution so we understand what's going on in terms of the computation and how it relates to the picture and how it relates to hypothesis testing. So now we're ready to move on to step 3. One of the things that we have to be aware of in step 3 is we have to know what our level of significance is. This is actually given to us in the problem statement. So this value right there, the level of significance, is our alpha value, and that represents the chance of committing what's called type 1 error. We'll talk about that later on. But the alpha value is the area in this tail right here where it's 0.05 for that area. And you can guess that the area in the fail to reject region would be 0.95. I'm not going to write that in there because we're really not going to reference that or use that in the hypothesis test at all. But the value of 0.05 is going to go in that left tail right there. So this is 0.05 for alpha. And then what we need to do is we need to calculate the test statistic and the p-value. The test statistic is simply a way to compare the sample proportion to the population proportion and account for the variability of the population. So when we calculate the test statistic, which I like to denote with a z star, that way we know it connects with the p-value with the p star there. And it's just for notation purposes because we've got a lot of p's that we're looking at in this problem. We have p hat, we have p sub 0. The p star just says that's the probability, the p-value. Just another easy way to identify that. But anyways, going back to the test statistic, we know all the values that we need, and it becomes really just a plug and chug problem at this point. So in the numerator, we have 0.70 minus 0.75. And then in the denominator, we have the square root of 0.75 times 1 minus 0.75, all divided by our sample size of 100. And if we do the math on this, I like to do it in two parts. In the numerator, that comes out to be negative 0.05 in the numerator. And then in the denominator, when I take the square root of that, that comes out to be 0.0433. And then last, if we divide those two values, the numerator by the denominator, we come up with a value of negative 1.155. And that would be our test statistic value. Now I'm going to go back to the picture and just kind of show you this, but that test statistic falls to the left of 0. Now here's the only problem. We don't know if that test statistic falls in the rejection region of H sub 0 to the left of that vertical red line or in the fail to reject region. We just know it's to the left of 0. We don't have a horizontal scale on here that indicates which area we're going to fall in. And that's okay because we're going to use the probability to help us figure this out. So really our test statistic Z could be any one of those places to the left of 0. So for right now, I'm just going to say our test statistic is on the left side, which is negative 1.155. Now we move on to the next step. We have to calculate our p-value, and we're going to use a function on the TI-84 calculator called the normal CDF function in order to do this. Look at my video on finding p-values, and you'll understand how to use that function and do this. So to calculate our p-value, we'll use that normal CDF function, and we have to determine whether that test statistic is a lower bound or an upper bound. And then the mean and the standard deviation are 0 and 1. Those are always what those values will be when we're dealing with the normal CDF and using it to find a probability. So this negative 1.155 is either going to be the lower bound or the upper bound. And I think the easiest way to determine that is to go back to this picture right here in step 2. So if you look at our test statistic where it's located, it's to the left of 0. In the alternative hypothesis, it says p is less than 0.75. So that less than sign is telling us we have to go from the direction of that test statistic to the left in order to find that area. So that means the lower bound is going to be the far left side, and the upper bound is going to be that test statistic. And if you have difficulty, remember the lower bound is on the left side. Just think lower is left, or you could think of it as the left bound. Now this curve goes on forever that makes up the normal distribution. We have a horizontal asymptote, so technically this lower bound is negative infinity. We just need to use a really small number so that way we get a fairly accurate probability. I like to use negative 1 million in the case that we have right here as my lower bound, and then my upper bound will be this negative 1.155. We'll go ahead and put that in there. So we have a negative 1 million, and then a negative 1.155, and then we have 0, and we have 1. And when we go and we use the calculator in order to generate this probability, we come up with a value of 0.1240. That is the probability that's connected to that value of negative 1.155. So if I go back over here to the picture, we want to think about that probability right there. And remember, that represents the area under the curve from this test statistic right here to the left. So that value of 0.1240 is much larger than this value of 0.05. So therefore, this test statistic has to be somewhere over here on the right of that vertical red line right there, because it has a bigger area than that. So I'm going to go ahead and erase this line right here in this bracket, and now we have a pretty good idea that the test statistic is right there, and then that p-value that we just calculated represents this area to the left of that vertical line that I drew in there for the test statistic. So this area that has the striped blue area, that is our p-value, which is 0.1240. And remember, we're talking about area, and that area is bigger. And don't get confused, because we're to the left of 0, the area should never be negative. Area is always positive, and probabilities are always positive. What should be negative is this test statistic, because when we move to the left of 0, we're talking about the horizontal scale and not the area. So right now, we know that we're going to fail to reject h sub 0. So visually, that's what we're doing, and then we'll take a look at this using the decision rule. So we already understand step 3. Let's go ahead and move on to step 4. The decision rule, since we use the p-value approach, is always going to be the same. So if you recall, we calculated our p-value to be 0.1240. We know that our alpha value, which was given to us, was 0.05. All we have to do is apply this decision rule that's given right below those values and determine whether we reject or we fail to reject our null hypothesis. So I'm going to ask you to make the statement of whether you reject it or fail to reject the null hypothesis. And then you also have to justify your answer by comparing those values. So an appropriate statement to make would be something like this. Since the p-value, p star equals 0.1240, is not less than our level of significance, alpha equal to 0.05, we will fail to reject the null hypothesis h sub 0. So this right here, the fail to reject, this is our decision. And then this beginning part right here, this is the justification for our decision. We compared the p-value to the alpha value, and we determined it wasn't less than or equal to our alpha value, so we should fail to reject our null hypothesis. Basically, I just negated the statement. So that brings us to the conclusion. When we write the conclusion, we want to go back and we want to use the jargon that was used in the problem statement and write the conclusion that somebody can understand it. So when I start talking about the conclusion, let me first write out the hypothesis statements. All right, and if you recall, the alternative hypothesis was derived from the problem statement that we were working with. When we went through and we did this process, we were testing h sub 0. And we determined that we're going to fail to reject h sub 0. So this one we failed to reject. And so what that means is there's not enough evidence to reject the null hypothesis, okay? In other words, if you think about this as a true or false statement, we could think of this as indicating that there is evidence or there's some information that tells us that this could potentially be true. And only one of the two statements can be true, and I think this is helpful for students learning intro stats, is if that's true, then this one right here, there's not evidence to support this. So we're just going to say that this is false. And we're looking at the statistical significance, okay? So when we think about this, I think this makes it easier to write the statement. And I like to use this generic statement that you see up above in order to kind of rewrite this. Remember, we want to write it in terms of that problem statement that we originally had, and we use that problem statement to derive our alternative hypothesis statement. So we're going to take this and translate it into information up here. And in general, I would recommend writing our alternative hypothesis right there. So this represents the proportion of people who will continue to watch a TV show is fewer than 75%. So we're going to go ahead and write that in words up here, that the proportion of people who will continue to watch the TV show is less than 75%. So I'm going to convert that from a decimal back to a percentage at this point. Now the only other thing that we have to do is we have to fill in this blank right here. You're either going to leave it empty or you're going to put the word not in there, all right? So if H sub A is false, that means there's not evidence to support this. So we're going to say there is not sufficient evidence to support that the population proportion of people who will continue to watch the TV show is less than 75% on average in the population. So that last statement that I underlined is really generalizing this out to the population, and it's saying the majority of the time this value of our proportion, our sample proportion, is not going to be smaller than 75%. So now we just made the decision based on statistical evidence. So hopefully this helps you with navigating hypothesis testing and gives you a little bit of insight on that. And like I said, we'll have future lessons where we talk about the case where we have a two-tail test. And we may come back and we may look at a right tail test as well, just to kind of refresh our memory.